You know how logical statements can sometimes feel like this tangled mess of ands, ors, and nots? It's easy to get lost. But what if you had a tool that could just slice right through all that confusion and give you a perfectly clear answer every single time? Well, that's exactly what we're going to build today.
All right, so here's the puzzle we're tackling in this explainer. When is the statement P or Q implies not R actually true? I know, it looks a little complicated, but I promise you, by the end of this, you'll be able to solve it with absolute certainty using a really powerful tool called a truth table. But hold on. Before we can start building anything, every good construction project needs a blueprint, right? We need to know the basic rules and the components we're going to be working with. First things first. So, what exactly is a truth table? Honestly, the best way to think of it is like a map for a logical statement. It literally charts out every possible path and every possible outcome, so we know exactly where an argument leads no matter what. No guesswork, just clear answers. And the structure is brilliantly simple. The columns are there to help us break our big statement down into small, manageable pieces, from the basic variables all the way up to the final expression. And the rows? Well, the rows just represent every single possible scenario, every combination of true and false you can think of. By filling it all out, we make sure we haven't missed a single thing. Now, here's something that's absolutely crucial. Remember PEMDAS from math class? Please excuse my dear Aunt Sally. Well, logic has its own strict order of operations too. We can't just solve things in any order we feel like. First, you always handle the negations, the nots, then ands, then ors, and you save the implications for the very end. Following this order is the key to getting it right. All right, we've got our blueprint and we know the rules. It is time for the fun part. Let's start the actual construction and build this truth table for our problem step by step. First, we got to build the frame, the skeleton of our table. We'll start with a column for each of our basic variables, P, Q, and R. Simple enough. Then we add columns for the smaller pieces inside the statement, in this case, not R and P or Q. And finally, we add the grand finale column for the entire proposition we're trying to solve. So how many rows are we going to need? Well, there's a super simple formula for that. It's just 2 to the power of the number of variables you have. We've got 3 variables, P, Q, and R. So we calculate 2 to the power of 3, which is 8. That means we need exactly 8 rows to capture every single possibility. Okay, now we fill in our foundation. And you might think this is tedious, but there's a really cool pattern, a little trick to make sure you get them all. For the first column, P, you just alternate every 4. 4 trues, 4 falses. For Q, you alternate every 2. 2 trues, 2 falses, 2 trues, 2 falses. And for R, you just alternate every single one. True, false, false. See? That simple pattern guarantees we've covered every combination without even thinking about it. All right, time to start solving. Thinking back to our order of operations, what's the very first thing we have to calculate? That's right, negation. So let's make our not R column. This part is super easy. We just look at the R column and flip every single value. Every true becomes a false, and every false becomes a true. Done. Next up on the list is the OR statement, P or Q. The rule for OR is pretty generous. The result is true if at least one of the parts is true. So if we look at the first row, P is true and Q is true, so of course P or Q is true. But look at the third row. P is true, but Q is false. Doesn't matter. Since P is true, the result is still true. It's only false when both P and Q are false, like you see down in those last 2 rows. And here we are, the final step. We're going to use the P or Q column we just made and the not R column to solve the whole thing. Now, the rule for implies can be a little quirky, so listen close. It is only false when a true statement leads to a false one. That is the single only time it fails. For example, check out row 1. We have true implies false. That's a broken promise, so the result is false. But look at row 2. True implies true. That's totally fine, so it's true. And what about row 7? False implies true. That's also considered true. In logic, you can't really prove anything wrong by starting from a false assumption, so the implication holds. And we did it. Construction is complete. Our table is finished. Now we can finally step back, admire our handiwork, and see what it tells us. It's time to find the answer to our original question. This is the real magic of what we just did. We took a confusing tangle of symbols and logic and transformed it into this perfectly clear, organized map. There's no more guessing, no more uncertainty. All the answers are laid out right in front of us.
So let's go all the way back to the beginning. When is our statement true? Well, the table gives us the exact answer. But you know what? It's actually easier to spot when it's false. If you look at that final column, you can see there are exactly 3 rows where it's false, which means our original statement is true in all of the other 5 scenarios. We've definitively solved the puzzle.
Okay, so you've seen how it's done. Now it's time to put your new skills to the test. Seriously, the absolute best way to make these concepts stick is to get your hands dirty and build one yourself.
Here's a new challenge for you. Can you build the truth table for this one? P or not Q implies P and Q. Go ahead and pause here and give it a shot. The process is exactly the same. Handle the negation first, then the stuff in the parentheses, and finish it off with the final implication. You've got this.
So what's the big takeaway here? It's that you are now equipped with an incredibly powerful and reliable tool. A truth table lets you take any complex logical argument, no matter how intimidating it looks, break it down into its core pieces, and analyze it with perfect clarity.
And that brings us to the coolest part. This tool isn't just for abstract, mathy problems. Think about the arguments you hear every single day, in the news, in advertisements, online. You now have a method to translate them into pure logic and test if they actually hold up. So I'll leave you with a question. What real-world argument are you going to test first?